40 gigatons.
Yeah, 40 gigatons.
Yeah.
It is a number that just sort of sits there on the page staring at you.
It is the number that keeps coming up in the margins of basically every climate report I have read this year. And for those joining our deep dive today, that is the amount of carbon dioxide we are currently pumping into the atmosphere globally every single year.
Right.
It is a number so large, it essentially breaks your ability to visualize it.
Oh, absolutely. I mean, it's a literal mountain of gas. If you somehow turn that into solid graphite, you'd be burying Manhattan entirely every few months.
That is a terrifying mental image. And usually when we talk about this on the show, about how we get that mountain back out of the air,
Yeah.
the conversation tends to drift toward the more romantic solution.
Yeah, the nature-based stuff.
Exactly. We talk about nature, we talk about rewilding, planting 1 trillion trees.
The whole gardener approach is very popular right now.
It is, because
Yeah.
it feels good. It looks great on a corporate brochure, you know?
Yeah.
But today, we are going to do something a little uncomfortable. We're going to look at the actual math of trees.
And we're probably going to find it wanting, which is tough because it's not that trees are bad. I love trees.
We all love trees.
Right. But the source material we're digging into today suggests that if we actually want to survive the next century, we need to stop thinking like gardeners and start thinking like miners.
So let's get into the source. We are breaking down a paper from 2026 by Ankamgullan Nisanjargal, and the title is, well, it's a bit of a mouthful, High-Efficiency Solar Thermal Electrochemical Synthesis of Carbon Nanotubes from Atmospheric CO2.
Yeah, it definitely does not roll off the tongue.
No, it doesn't. But hidden in that very dense academic title is a claim that is frankly startling. We are looking at a technology today, specifically the solar thermal electrochemical process, or STEP, that claims to be 100 times more efficient per acre than a forest.
100 times. And crucially, it doesn't just bury the carbon either. It doesn't just pump it down into an empty oil well and hope it stays there for 1,000 years. It actually turns the CO2 into something that is worth more than gold.
See, that is the hook for me. Turning a costly waste product into a luxury industrial good.
Exactly.
So let's strip this down. We need to understand the machine, the math, and the money here. Let's start with the machine. What does a solar thermal electrochemical reactor actually look like? Because when I hear solar, I'm picturing shiny glass panels on a suburban roof. But that is not this, is it?
Not even close. If you put a standard solar panel next to this device, the panel looks like a toy. This is heavy, heavy industry. The core of this beast is essentially a crucible.
A crucible, like a giant cauldron.
Basically, yes, a massive high-tech cauldron specifically designed to hold molten salts. We were talking about lithium carbonate or, more recently, strontium carbonate electrolytes. When I say molten, I don't mean warm. I don't mean boiling water. This is a literal lava bath.
Wow.
The operating temperature is sitting right between 750 and 800 degrees Celsius.
Okay, wait, why does it need to be that hot? Because I thought the goal was just to capture gas out of the air. Why are we simulating a volcano?
Well, because CO2 is incredibly stubborn. The chemical bond between the carbon atom and those two oxygen atoms is one of the strongest bonds in nature.
It really doesn't want to let go.
It really, really does not want to break apart. So if you want to rip that carbon atom away, you need a highly energetic environment. You need the salt to be liquid so the CO2 can literally dissolve into it.
Oh, I see.
It's almost like sugar dissolving into a hot cup of tea. If the tea is freezing cold, the sugar just sits at the bottom doing nothing. The heat forces the reaction.
Okay, so we have this vat of liquid angry salt. Where does the solar part of the name come in then? Because usually solar just means electricity to me.
Right, and this is the first real stroke of brilliance in the design. The system actually uses the sun in two distinct ways, completely simultaneously. First, it uses concentrated solar power, so huge arrays of mirrors, to focus infrared radiation directly onto the crucible.
So the sun is acting directly as the furnace.
Exactly. In older methods of electrolysis, you'd have to burn natural gas or pull huge amounts of grid electricity just to melt the salt in the first place, which completely defeats the purpose of carbon capture.
Because you're creating a massive amount of emissions just to capture emissions.
Exactly. It's a net loss. But here, the heat is completely free. It's just mirrors. But then, on top of that, it also uses concentrated photovoltaic cells to harvest the visible light spectrum from that same sunlight.
Oh, to generate the electricity you need for the actual reaction.
Right. So you have the raw heat to melt the salt and the electricity to run the chemistry. It utilizes the full spectrum of the sun. It's a hybrid engine.
That makes a lot of sense. So what happens when you hit that dissolved CO2 with the electrical current?
That's the electrochemical part of the STEP acronym. You apply a low voltage current, We're talking about zero point 0.8 to 2.0 volts across 2 electrodes submerged in the molten salt.
And that's enough to break it.
With the heat, yes. That electrical shock splits the molecule right open. Pure oxygen bubbles off the anode, which is a really nice bonus, by the way. You get pure O2,
Yeah.
and solid carbon starts to physically grow on the cathode.
It honestly sounds like industrial photosynthesis.
It really is.
Yeah.
But it's photosynthesis on absolute steroids. Biological photosynthesis is slow, it's gentle, it works at ambient temperatures. This is brute force thermodynamics. It just strips out all the biological limits.
But here's where my skepticism kicks in a bit, because we've known about electrolysis for a very long time. We've known we can split CO2 in a lab. So if this is just a really hot battery, why hasn't this taken over the world yet? What was the bottleneck preventing us from just doing this 10 years ago?
That is the billion-dollar question. And usually the answer in any chemical engineering problem comes down to surface area and thermal stability.
Okay.
Think about the cathode, the metal plate where the solid carbon is growing. In a standard reactor, you were growing that carbon on a flat metal plate. Think of that flat plate like a parking lot.
Okay, I'm with you. A parking lot.
The carbon atoms coming out of the solution are the cars. They need a place to park. But once every single parking spot on that flat plate is taken, you can't park any more cars. The reaction completely stops.
Right.
You literally have to shut down the machine, cool it, scrape the carbon off, and restart. It's incredibly inefficient.
So the limit isn't the chemistry itself, it's the physical real estate on the electrode.
Precisely. And this is where the paper takes a turn that I honestly did not see coming when I first read it. To solve this very physical, industrial hardware problem, Nanotubes didn't just add more pipes. He didn't build a bigger salt tank. He used geometry.
This is the fractal part of the outline that I was really struggling to visualize. The infinite fractal descent framework, or IFD.
Yes, IFD.
Because I think most of us, we know fractals as those trippy computer screensavers from the 90s, or maybe like the shape of a snowflake or a coastline.
Yeah.
How does abstract mathematical geometry help us catch physical carbon?
Well, you mentioned coastlines, and that's actually the perfect analogy. Think about the coastline paradox. It's a very famous math problem. If you measure the coast of Britain with a mile-long ruler, you get one specific length.
Right.
But if you measure with a flexible tape measure, tracing every single little inlet and every single rock, the coastline suddenly gets much longer.
Because you're including all the tiny nooks and crannies that the big ruler just skipped over.
Right. And if you go even smaller and measure around every single grain of sand on that beach, the length of the coastline becomes almost infinite. Nanotubes applied that exact logic to the electrodes in the salt bath.
Oh.
We didn't use a flat metal plate. They used something called a topological scaling operator to machine the cathode with a fractal pattern. It creates ridges on ridges on ridges, physically descending from the macro scale all the way down to the micro scale.
So they are artificially making the coastline of the electrode infinitely long just to create more parking space for the carbon.
Theoretically infinite, yes. In practice, they push it to what the paper calls the octave breaking point. This is a critical threshold where the physical geometry of the metal perfectly matches the exact size needed for carbon nanotubes to self-assemble.
So by making the surface rougher in this very specific mathematical way, they are creating more spots for the carbon atoms to land.
Orders of magnitude more. They are creating millions of nucleation seeds. These are tiny spots where the carbon can latch on and start growing. It turns a flat, inefficient metal surface into this hyperdense carbon sponge.
And does this fractal design fix the heat problem too? Because I imagine keeping a giant tank of salt at exactly 750 degrees is pretty hard when a cloud passes over the sun. Solar power is notorious for flickering.
That's the other side of the fractal coin right there.
Yeah.
They use what they call fractal octaves for thermal distribution.
Okay.
Instead of just heating the pot from the bottom like a tea kettle, the heat transfer system inside the crucible branches out geometrically. It looks almost exactly like the blood vessels in your body.
Oh, like a lung.
Exactly like a lung. Your lungs are biological fractals. They branch from the trachea to the bronchi down to the tiny alveoli just to maximize the surface area for oxygen exchange. This reactor does the exact same thing, but for heat.
Wow.
It ensures there are zero cold spots anywhere in the salt, even if the solar input fluctuates because of a cloud. The fractals act as a massive thermal buffer.
It's just fascinating that we are literally using designs from biology lungs, vascular systems, to beat biology at its own carbon capturing game.
It really is. It's biomimicry, but built with titanium and molten salt instead of soft tissue.
Okay, so we have a super efficient, Fractal enhanced lava bucket. We are sucking CO2 out of the air. But we aren't just making dusty lumps of coal here, are we? The paper talks extensively about carbon nanotubes.
Yes, this is the assets part of turning air into assets. We are synthesizing graphene nanocarbons, or GNCs. These aren't charcoal briquettes you throw in a grill. These are extremely high-fidelity structured materials.
Because I saw a whole menu of different materials listed in the source. Can you break down the difference? Because to a layperson like me, carbon is just carbon.
Oh, it's definitely not just carbon. It completely depends on how you tune that electrical current and what specific metals you use for the electrodes. First, you have standard carbon nanotubes.
Okay.
These are tiny cylinders of pure carbon that are significantly stronger than steel but lighter than aluminum. You can use them in airplane frames, suspension bridges, high-performance concrete.
Basically the ultimate building
It's
materials.
the absolute best building materials we have. But then the paper talks about carbon nano-onions.
Please tell me that is a real scientific term.
It is absolutely real, I promise.
Yeah.
Imagine concentric hollow shells of graphene nested one inside the other, exactly like the layers of an onion. Because they are perfectly spherical at the nano level, they roll over each other without any friction.
So they act as lubricants.
Incredible lubricants. They can replace carbon black in car tires and heavy machinery. But unlike traditional oil-based lubricants, they don't break down under heat the same way. They are incredibly durable.
And what about the magnetic CNTs? That sounded like science fiction.
This one is incredibly clever. If you use an electrode that contains iron, the carbon nanotubes will naturally grow around tiny microscopic iron particles. That makes the entire nanotube slightly magnetic.
Oh, which solves the collection problem I was wondering about earlier. Because how do you get tiny carbon dust out of a vat of 800-degree lava?
Exactly. You don't need some complex filter that's going to melt. You just turn on a strong electromagnet and literally pull your finished product right out of the molten salt. It simplifies the entire manufacturing chain down to the push of a button.
That is wild. And there is a very important distinction here regarding the broader fight against climate change that we need to hit. When you and I plant a tree, that tree holds carbon for, what, 80 years? Maybe 100 if we're lucky.
If you're very lucky. And that's assuming it doesn't rot or get eaten by bark beetles or burn down in a massive summer wildfire. Trees are temporary storage. It's a biological cycle. Carbon goes in, carbon eventually comes right back out.
But these nanotubes.
These are structurally stable on geological timescales. We are talking millions of years. Graphene does not rot. It does not burn easily at all. Once you turn atmospheric CO2 into a nanotube, that carbon is locked away. You have effectively removed it from the atmospheric equation permanently.
So let's get to the showdown then. The paper explicitly pits this technology against natural forests in a section called Economic and Spatial Feasibility. Now, as a lover of hiking, I like forests. But what do the actual numbers say?
The numbers are pretty unsentimental. Let's look at 1 standard acre of land. If you plant a dense forest on that acre and you wait 20 entire years for it to mature, you can remove roughly 2 to 5 tons of CO2 from the air per year.
2 to 5 tons. Okay, that's our biological baseline.
Now take that exact same acre, put it in the middle of a desert so we aren't even competing for good arable farmland, and fill it with these IFD-optimized step modules, specifically the Genesis kiln models they mention in the source.
How many of these kilns can we fit on 1 acre?
You can pack about 4,000 modules onto a single acre, and that 1 acre will remove approximately 200 tons of CO2 per year.
200 tons. So it is literally 100 times more effective square foot for square foot than nature.
And it starts working on day 1. You don't have to wait 2 decades for the factory to grow up.
Now, there was another major efficiency leap mentioned in that section, something called the Genesis DJ design. Now, DAY is direct air capture. I always hear from climate skeptics that DAY is too energy hungry to ever work because you have to process so much empty air just to find the carbon.
Yeah, that's the classic engineering critique. Usually in traditional DS, you have to use giant fans to suck in massive volumes of air and heat all of it up to separate the CO2. But our atmosphere is mostly just nitrogen and oxygen. Heating up tons of nitrogen is a massive waste of energy.
It's like boiling a giant pot of water just to cook one single pea.
Exactly. Bad cooking, bad engineering. But the Genesis D design solves this. It uses an advanced membrane system that pre-filters the ambient air. It physically isolates the CO2 molecules before they ever enter the heat chamber.
Oh, so the reactor only ever heats the pure CO2.
Right. It drastically cuts the energy penalty. You're no longer paying to heat up dead air.
I want to touch on one specific number from the paper because it sounded very sci-fi to me. The universal scaling factor. Gamma equals approximately 1.83. What does that actually mean for us non-mathematicians listening?
Okay, so this is the theoretical ceiling. In physics, there is often a hard limit to how good a system can possibly be. The universal scaling factor represents the strict atomic limit of how many nucleation sites, those little parking spots for carbon, you can physically pack into a three-dimensional space.
It's kind of like the speed of light, but for carbon capture efficiency.
Essentially, yes. And the paper argues that by using this fractal design, the reactor isn't just a little bit better than older models, it is pushing right up against that gamma limit.
Meaning?
It implies we are reaching the absolute maximum possible efficiency allowed by the laws of physics. We are moving from capturing a few thousand tons in pilot plants to capturing actual gigatons.
Which brings us to the reality check. Because I can hear you, the listener, right now saying, well, this sounds great, but is it vaporware? Is this just a fancy PDF with some math in it? The source is from 2026. Is this thing actually built?
It is built. It's running right now. The paper specifically cites a live facility at the Shepherd Center Natural Gas Power Plant up in Calgary.
Calgary. Okay, so right in the absolute heart of Canadian oil country.
Which is poetic, in a way. They have individual kiln modules running there right now that are already capturing 100 tons of CO2 per year each.
So this isn't a tiny lab bench experiment with a beaker. This is real industrial hardware.
Real hardware. And there's a vital note in the paper about the core materials changing in 2026, which is what makes this viable now.
Right, the shift to strontium. Because originally they used lithium carbonate electrolytes.
And we all know lithium is incredibly expensive. Everyone on Earth needs it for electric vehicle batteries.
Exactly. Competing with Tesla and Ford for raw resources is a terrible business model for a startup.
But the massive 2026 breakthrough was switching the salt bath to strontium carbonate blends.
Strontium. That honestly sounds like a fake metal from a comic book.
I know, but it's just another alkaline earth metal salt.
Yep.
More importantly, it is about 10 times cheaper than the lithium blend. That completely collapses the capital expenditure required to build these things. It makes them cheap enough to mass produce in factories and just drop into deserts all over the world.
So we have the proven tech, we have the real-world location, and the cost of building them is actively plummeting. It really feels like we are on the verge of a genuine paradigm shift here.
I think paradigm shift is exactly the right term. Look at the last 40 years. We have culturally viewed CO2 strictly as pollution, as trash. It's a cost on a ledger. It's an environmental sin.
A literal tax on human existence.
Exactly. But the STEP technology completely flips the board. We aren't just burying waste anymore. We are manufacturing highly desirable goods. We are mining the sky.
You know, it reminds me of the history of aluminum. Back in the day, Napoleon III used to eat off solid aluminum plates to impress guests because it was considered rarer and more valuable than gold. Yeah. Then we figured out how to use electrical electrolysis to extract it easily, and suddenly it's so cheap we wrap our leftover pizza in it and throw it away.
That is the perfect parallel. We currently have an unlimited, suffocating supply of carbon sitting in the atmosphere. The bottleneck was never the lack of material, it was always the lack of a viable method to extract it. By combining the brute force physics of solar thermal energy with the abstract mathematics of fractals, we're finally unlocking that resource.
So, if we play this forward a bit, if this actually works at the global gigaton scale the math suggests, the entire climate narrative changes. It's no longer just about saving the planet by doing less, by traveling less, consuming less, shrinking our footprint.
No, it's about doing more. It suggests a very near future where high-tech industry and environmental stewardship are the exact same thing. You clean the air because it literally makes you rich. And honestly, that is probably the only human force strong enough to actually move 40 gigatons of gas. Profit.
It's a surprisingly hopeful vision, a world where the giant industrial smokestacks are actually the intake valves for the clean factories of the future.
And where the physical materials we build our civilization with, our future skyscrapers, our airplanes, our bridges, are literally made out of the exact same pollution that used to threaten our existence.
I really love that. But before we wrap up today's deep dive, I want to leave you with a thought that came to me while I was reading the end of this paper. We've spent my entire life talking about CO2 as the ultimate enemy, a dangerous surplus we have to get rid of at all costs.
Right.
But if this technology takes off the way the math says it will, and if carbon nanotubes truly become the most valuable foundational building material on Earth, what happens when we actually run out of pollution?
Man, that is a wild thought experiment.
Think about it. Imagine a world 50 or 60 years from now, We've successfully scrubbed the atmosphere all the way back down to pre-industrial levels. We fixed it. But the massive global factories still desperately need airborne carbon to build the next generation of spacecraft or fusion reactors.
You're talking about a peak carbon scenario, but completely in reverse. A carbon shortage.
Exactly. Will we see a future where nations are aggressively competing to harvest the remaining CO2, where the literal air over a country is considered a fiercely protected sovereign mineral resource?
Well, if the sky is a literal gold mine, people will absolutely fight over who holds the mineral rights.
It puts a whole new spin on the phrase protecting your airspace.
It certainly does. It implies a crazy future where a clear blue sky isn't just a nice day, it's a measurable asset on a national balance sheet.
Something to mull over as you look up today. That is it for our deep dive into the fractal revolution. Thanks for joining us.
Keep looking up.
We will see you next time.